My name is Eric. I'm one of the founders of a company called Generable. We do work in early and mid-stage clinical research, basically preclinical, phase 1 and 2 clinical trials. This talk is going to be about some use cases in productizing STAN. I don't even know if it's a word, productize something. We're also going to have, so I'll go for a little bit, maybe 30 minutes, then Markus is going to do a bit, and then Anna from Lendable, and then if we have some time, we'll have like a panel discussion as well. So that's the plan. Work. All right. So productizing STAN, it's kind of a dry subject. So we'll spice it up a notch, as they say in the US. Does anybody work in finance? Anybody works in finance? You guys know what this is? Have anybody seen this formula? It's like one of the most elegant models that came out of quantitative finance in 70s. This guy is Bud Fox from the movie Wall Street. Yes, sir.
Sorry, I'm interrupting.
No worries.
Can you just drop 5 to 10 minutes before 6:20, 25, because then right after this one, right?
Okay.
So that the people can move. Yeah. Sorry.
No problem. Okay. So the question that I asked is like, why do we want to productize anything? And so this is kind of my lead up to trying to answer this question. And so in about 1970s, there's a paper that came out that described this model for pricing call options. And shortly after, Chicago Board of Options Exchange started trading these products. Now the traders that kind of look like this, they don't really understand, nor do they particularly care about partial differential equations that give rise to this kind of model. But yet they do use them, the model that is, in their daily work. And to use them successfully, they have to observe how this model works under different conditions. And by this time, at this point, like this model has been fully socialized, meaning that people have used it enough so that they kind of understand what it does. And they know when it works well and when it doesn't work well. And this is kind of my pitch to people who develop models is like, we got to put them in front of users so that these models can get better over time, so we can actually test them in real conditions. There's lots of benefit to doing that. In our field, where we work in clinical research, sometimes people make decisions on whether or not to, let's say, switch somebody in to a different trial arm, right? So you have like an oncology trial, and they measure, let's say, tumor sizes over time. And the common thing there is to say, well, if the tumor is reduced by 30%, we sort of declare that this treatment is working, or if it's increased by 30%, they declare progression of the disease. That's a raw data decision, right? Which is nice on one hand, you just observe the data. On the other hand, that's kind of a problem, right? Because there's lots of measurement noise in it. If you just use that, you're going to be whipsawed. So your decisions will be sort of whipsawed around. So you want to say, well, instead of that, we'll say, what is the probability that a tumor size will be increased or decreased by 30%? That's better, but then now you're asking your user to accept your model, right? And why should they? Why should they believe you that this is a good model, in fact? So on one hand, we think the model is great, but you have some convincing to do. And so it's always on us, I feel like, the people who develop models, to do that convincing. And the only way I know of of doing it well is to expose the model in front of those users and let them use it a lot, right? So, you know, unlike people in finance, we tend to work with the models like these, which if you went to Daniel's talk earlier, he was talking about ordinary differential equations. And so we, you know, this is a common model that we see in pharmacometric research where we observe some concentration of compound in blood. And there's a model for how it transfers between compartments. And there's some statistical distribution around it. And that's like really cool that we can do that in Stan. So the rest of this, hopefully I set this up and gave enough reasons to why should we actually do this. So the rest of the talk, I'll touch a bit on the Bayesian workflow, which you might have seen already if you came to Jonah's talk, he probably talked about it. Talk about more of the like a practical goals of productization, the tactical goals. And then we'll describe like an infrastructure that we use at Generable to do it. And then we'll have a couple other talks and we'll see if we get to the panel. Hopefully we will. Right. So this is a typical picture that I show for the Bayesian workflow in a sense that the interesting part is this formulating of generative model. And that often takes a long time, right? Particularly if we're working with complex models like OD models, they take a long time to fit. And so it's a little frustrating, right? I have a model maybe running for like 2 days. At the end I find out it's not so great. Well, I just lost 2 days. That's annoying, right? So we try to solve this part by having an infrastructure where we can fit lots of those things simultaneously on a cluster somewhere, and hopefully speed up the process. You know, also, I think in Dan's talk, if you saw, there's now a nice interface that Sebastian Weber from Novartis mostly developed to allow us to do multiprocessor interface MPI. So a lot of this stuff, is just getting to the right model, to simulating lots of data, recovering parameters, and so on. And then, you know, we, of course, we do lots of model fitting. Here we try to we sample from the posterior predictive distribution, right? And we try to save that distribution so we know what happens to it. And which data belongs to which posterior and which model. And then there's also typically a decision problem. So this is often an overlooked part of the workflow because in statistics, you know, people oftentimes just end with the inference, right? We've got some parameter estimated, maybe we made some predictions. But in the kind of work that we do, there's a decision that needs to be made, and that decision involves some kind of trade-offs. Maybe there's a trade-off between an efficacy and toxicity of treatment. And so we need to evaluate those decisions in a principled way, and this is where the Bayesian decision analysis comes in very handy. So there are a number of goals that you may have for doing productization. I'll point out the ones that we care about. So some people try to automate model construction. So actually creating models, like packages like RStanArm and VRMS do some of that. There are some people who think about like developing graphical interfaces for model constructions. We don't do that, so we don't focus on it. We just stick to Stan. We do enable model fitting in a pretty fast way. Also maintaining posterior database. That's something that if you're fitting lots of models, it's an administrative issue. You have now, 20 different distributions from different runs, like which one is the one I need. In regulated environments, that becomes a big deal. And then, actually deploying these things into production. And there you can imagine two modes of operation. You might deploy it for interactive use. That's largely our use case. Or you can be deploying it for automated decision making. So people who work in sort of higher frequency domains in finance or on advertising or so on will oftentimes do this kind of thing. We tend to focus on the interactive use. Right? So in order for us to do our job better and exposed to these posterior distributions to decision makers, we're developing this analytics stack on top of AWS. There's two main components. The one I'll talk about mostly is this elastic compute service, and it really set up to accomplish these four major goals. One is I alluded to earlier, which is the provenance of the posterior distribution, right? Which model and data give rise to a specific posterior. Scalability is another one, sharing, collaboration, and reproducibility. In order to make this thing tractable, we, sort of on the cloud, we build out this analytics context. So we have a concept of a user that has some permissions. And then there are programs and data sets that live within an analytics project. So you set up a project. Each one of these guys, so one instance of a program, one specific instance of a data set, results in a run. And a run then results in a number of chains that come out, which is actually your output. And so a unique run was determined by the data program and the run arguments, right? So those would be like maybe some initial conditions or other meta parameters. In terms of the access patterns, we developed a pretty simple management console, like a web UI that tells us what's going on. Also, it's an AWS infrastructure, so you can look at it from AWS console. There's a REST API that's like a thin layer over the infrastructure that can be consumed pretty much by any language. We have developed an R package, which I'll show, but you can easily do that with other packages as well, or other languages. So to give you an example, without like running anything live, because that's scary, we load up the R library, because there's remember a user context, so I connect with a username. When I type this in, it'll prompt me for a password. And once authenticated, I'm now in my context, and then I can do like, show me all the projects that I've been working on. And so this goes out in AWS and pulls out the names, descriptions of all the different projects. Right? Each object gets a unique hash. Then we could access each individual run. So if the run already completed, give it a name, we open this project. We have this function get run, and then you could take a look and see what has been run. So this was this project page poster. It's the poster we did for Page Conference, had 4 chains. Here's the number of iterations, and it says that all 4 are completed. Pretty easy. Similarly, you can get the actual listing of the program, right? So you get a program ID, call it, and then we could actually cat the program so we can see exactly which stamp program was used to make a run. And you can have like these help us summary functions, like similar to what you see if you use like an RStan or something like that, where you can get like summary of run statistics and so on. And of course, there are extract functions that let you access each individual parameter. So here I'm extracting this parameter theta12, take a look at it, and then you can use all of the tools that you're familiar with in R or wherever you're working to display. Let's here we just draw a histogram of this CL parameter using base plot. Good so far? And of course, if you haven't had any projects, we can go and create a program. So you can load one from a stand file. You can create that stand file anywhere you like. Read the data in, and then create the data set. This puts the data set out on AWS, and then you call this function called create run. So the cool thing is these are all non-blocking calls, right? So unlike, let's say, if you're in RStan or something else where you call sampling or some other function that it just like executes and blocks you, this thing it returns immediately and it does its thing. What kind of thing it does? It'll go out there. It'll spin up as many compute nodes as necessary to satisfy this task. It's not going to bother you. You can get a status of these runs by doing like this get run, or by going to an interface like this. So we could go to our API interface. So you can see all the projects that are available. You click on current, it'll show you things that are currently sampling or in process. It'll give you a quick summary of what's going on. Also, you can use the REST framework, sort of a raw REST framework, these are the RESTful APIs on AWS to look at the objects. And these are, in fact, the ones that are being consumed by the package that can develop. It's another way to look at it. And of course, like the cool thing is that once that is done and this posterior distribution is created, we can then deploy it, and then we could run and develop applications on top of it for use for people who are not specialists. So this is just as an example of one such simple application. This happens to be a clinical trial for non-small cell lung cancer. It had two arms. There's a standard chemotherapy arm and a targeted therapy arm. The measurements for those of you who are not familiar with solid cancers, the way they do measurements is this is a scan. It's a lung scan. What they do is the patient comes into a clinic and they measure a number of baseline tumors that they identify. The way they measure it is they take a longest diameter. So you see skin of this tumor is irregular. Take the longest diameter. They identify, let's say, 5 tumors that they're going to track. They sum it, and that becomes your measurement. So when it says SLD, this is the sum of longest diameter of baseline tumors in millimeters. This is the part that I sort of, when I started this talk, I alluded to earlier in saying, well, this measurement is noisy. You can see how that is, right? Like, first of all, these are highly irregular. They're also obviously not invariant to the axes of the imagery, right? So you take it from a slightly different angle, you get a different result, right? Which is why we kind of need a model. And so in this sort of application, this is a model that tracks a survival probabilities for each individual, and they have a submodel for each tumor. So this is what's in survival literature called joint model of tumor dynamics. So here we actually making a prediction for tumor progression for each individual patient, and that has some influence on their individual survival curves. So you can sort of like play with this kind of application, interact with, make predictions, and so on. And that's all I have for you. You got any questions for us or me, feel free to ping us on Twitter. Dan and I are both pretty big into Twitter. We just also just launched this new Twitter account called Bayes Dose. It's like a daily snippets of some Bayesian goodness. So check it out. And that's all I have.
Hello, I'm Markus Ojala from Smart.io. So today I will talk to you about one of the use cases that we have been running with Stan, so in production, so Bayesian revenue estimation. This is actually quite old project already, so we have been running this for 1.5 years. So it runs actually a daily for about 1,000 customers. There is old blog post if you are interested with more details, what we have been running, how we actually, what is the code and everything detailed. So, and I'm very favored to be referred by Andrew Gelman also for this blog post, and there are those jokes about that. So I will go through the use case, so you get context of what we are doing, and then also what are our learnings in productizing Stan to get it working. So to first understand what we are doing, so you understand the use case and how we solve it. So what is Smartly? So we are Facebook and Instagram marketing partners. So we help the world's largest advertisers to basically make their online advertisement and then optimize also the results. So through us goes about 1 billion yearly already. So that's a huge percentage of Facebook spend already. So it's like money going through Stan. So I'm not sure, it might be one of the biggest money-wise use cases for Stan at the moment, but I don't have the details. So I joined 3 years ago, we were 20, now we are 250 globally, growing fast still. So about the use case, what we are solving, so budget allocation. So if you are doing online advertisement, you have a lot of campaigns. So of course you're targeting maybe different countries, you have different promotions. There are 4 main parameters when you are doing advertisement. So it's budget, how much money you are putting to some ad. Then you have the audience who you are targeting. Then the creative, what you are showing to them. And then also bid amount, how much you are willing to pay for showing that. So that budget and bid, they are basically comparable, so they affect the delivery. So then the main question is, of course, that hey, I would like to put my money on the ad that brings most of my best results to the customers. So you have a lot of campaigns running and you would like to allocate the money to the best creative or ad. So we have implemented this kind of predictive budget allocation. So this is the tool how it's shown to the user what we have. So 1.5 years ago we only allowed optimizing towards conversion. So conversion can be, for example, purchase on web page. So how advertisement works, you see an ad on your Facebook news, so that's an impression, you click that, you end up on the web page, maybe you view some products, then you add something in the cart, you do a purchase. Purchase is a conversion, and then that purchase brings you revenue, maybe it brings you profit. So that's quite long conversion funnel. So what we ask from the user is that what you want to optimize towards. So for example, the conversions towards the pixel event purchase, and then we just try to maximize the purchase amount that you get from those conversions. So before 1 year ago we had all that conversion, now we have revenue optimization. So that revenue part, so if you click that on the UI, so that runs Stan in the backend then every night. So then what is happening? So let's go, so of course that one part is using Stan, so but what are we in overall doing? So we do multi-arm bandits. So basically that's the nice name which Gelman recently said that it should be just called explore and exploitation problem, because he didn't like the multi-arm bandit. So it's basically the idea is that you have few campaigns, maybe 10 campaigns, you don't know anything in the beginning. They refer to those gaming slots where you don't know anything, so arms. How do you do it? So you just start to put spend on some of the campaigns, and then you start to observe. You get impressions, you get clicks, you get conversions. The more you learn, the better you know. So, and then there is this kind of basic theory, how you should, what is the optimal strategy in this kind of games. So we use this Bayesian bandits Thompson sampling. So the number of pulls for a given level should match its actual probability of being the optimal level. So basically that corresponds to our case, so the proportion of budget for a campaign should match which is probability of being the best campaign. There are a lot of complexities that come with this, so when you change the budget, when you change things, so that affects the performance, so you can just like do it as simply. But the basic idea is that, hey, we have this rule, so we could also use it for budget analysis. So now we get to this, what should we do? So we should sample from the posterior of the mean of each level. So we should sample from the posterior of the predicted amount of conversions per spend for each campaign. And based on that, we can do the sampling, or the allocation. So then we get to this, like how to model the results or purchases per spend that you get per campaign. So as I said, so in advertisement that like funnel or the data process goes, so you see an ad or you actually spend money first to get an impression to that. And then people click, they do conversions, you get revenue, you get lifetime. The issue with this type of funnel is that it's very common that you have a 10 million audience, maybe 100,000 or 1 million see your ad. Out of those 10,000 click the ad, maybe 1,000 view some products, 100 do some add to carts, 10 do a purchase. So you get only 10 purchases, maybe a day, maybe a week. So the amount of purchases starts to be quite low. And when you go from that purchase towards revenue, so from those 10 people, maybe 9 bought with 10 euros, 1 bought with 1,000 euros. So there is a lot of like random variation happening the more you go to the right end. Left end has a lot of data, but it's far away from your like actual interest what you are doing. But you still would like to do the decisions on that low level, so react fast. So, but that's like so then you really need to model it well so that you are actually understand all the uncertainties that there are in this side. So as said, so we earlier supported optimizing towards conversions. So conversions is much easier case than the revenue. So conversions you can model it as POS or NetBin or some other distribution, and that just counts. So with counts, it's quite much easier. So that conversion model we had just like implemented ourselves directly in Python. So sampling from a lot of tricks just to like understand what is the model. So we had a very good model for estimating the cost per action, so conversion per cost. So model for that. And now we wanted to move towards optimizing the revenue per cost. So that's ROAS, return on ad spend. So how we can move to that part? So we just like model it separately. So we understand that funnel, how people move in the advertisement. So we think that, okay, maybe most of the ads actually, it's about just bringing the conversion and then people, the amount of revenue that comes per conversion. So that's a separate thing. So we could model that per ad. So the old data for modeling the amount of conversion, so that had a lot of data. It varies fast. It's maybe bigger differences. So it's also like the closer we are to the ad, the bigger impact it has. So you could think also that the revenue, we are already quite far from the advertisement that we have seen. We are interested in actually like knowing how much the advertisement affects to the revenue. So if you look at revenue per conversion, so maybe the advertisement didn't have any effect of that. It was more like that you just ended up doing a purchase, and then after what came as revenue, it's just like, okay, the advertisement itself didn't have an impact. But there are, of course, campaigns. Maybe I'm showing something so where there is a true impact. But we should basically be able to take those away so that the user doesn't have to do it. Because what we see is that people overreact to things, and our purpose is to take that kind of overreaction away. And it varies maybe much slowly. So little amount of data varying slowly, but still there are a lot of like raw differences, which most of them are just like random. We should model that away and get it working. So we have that this new model now, which we are going to implement in Stan, basically. So this is the part we do in Stan, and everything else is old. So we can plug in this and get it working. So then, like, how do we model the revenue per conversion or per purchase? So So this is the whole idea. Here we can use hierarchical models. So the idea is that there are so little amount of conversions per single campaign, single ad. And okay, if there is this 1,000 purchase or 10 euros purchase, so it might have happened in some other ads. So we can use this kind of hierarchy. So there is the whole advertisement about your campaign and then single ad. So maybe the single ad is similar to the other ads in the same campaign if they don't differ. So that's like that. By default, we assume that they are similar. So then, of course, revenue, it can follow any type of distribution. Log normal works for us already pretty well. So that's like a realistic case. So there is a lot of variation. So use that. And one complication for us, there are many related to advertisement, but one is that we don't observe individual purchases. So we just see aggregated data. So now we have hourly aggregate. So we see how many people did the purchases during 1 hour and what was the total revenue. And okay, that brings quite a lot of complexity. So we cannot model it directly as log normal. So we use kind of approximation. So we have model for single revenue per conversion, and then we can turn that model into like what is the sum of those events. So it's another log normal with transform parameters basically. But that already gives the reason why we need more of standard. Why can't we use ready-made models for log normal or something else hierarchical? Because our target parameter, it's not like direct log normal. So we have a transform target parameter that we need to tune a bit more. Then we have a hierarchical model. We have a lot of things going on that we want to do. So we need a custom thing. Of course, we could build something in Python as we have done for other parts, but this starts to be already an area where it's like nice to be able to just write your model, which is quite simple, but then if you wouldn't implement everything, so it gets quite nasty. So Stan was always on the list that I would like to do it in Stan and then find a use case. So this was very good narrow use case that Stan fits very well how to do it. So then we get how to solve this kind of issue with Stan. Like more kind of how did we do it? So we, of course, you start with something simple. So you start without those hierarchies. So there is this hierarchy. So just fill in how many observations there are, and you do something very simple. You trust that the Stan will work, which usually doesn't do in the first place. So we have this like observation that there is this like long part in the code which is about that transformation that I mentioned that we need to do. So that takes into that account. So we basically per ad set, that's the term where we are trying to estimate. For that we are trying to estimate the average revenue per conversion distribution. So then when you do that kind of model, so when you want to run it in production, so we have like 1,000 customers, they run a lot of campaigns, and we would like this to work for all of those campaigns. Some of those customers, they get just few conversions, some get a lot of, some have very different revenue distributions. So we would like this model to work for all of them automatically. So how to get that kind of working is, of course, you take some data set first that you just start feeding the model manually. Then you get your model working with that first. Then you take a bit more data set so that you can look. So what I found very useful was that I actually produced like PDF plots automatically about like 100 different cases, so that I can actually see different real cases, run the model through all of those cases, and find out differences. So like this kind of that, hey, my model didn't actually fit in this case. And initially, of course, there were a lot of errors that I'm totally out of that scale. Maybe something else. So then you start to fix those and identify. Then soon you get to the stage that there is maybe only like a few % of your cases don't fit. Something like that. Then you can look those. But you could maybe do some automatic checks or numeric calculation to identify those. But I found it very easy, like visually, even though you have 100 pages, you just click them through, and IE is very fast catching those in the developing mode. So, and the basic goal was that you should get your model work with all of the data sets that you have, which are very different, and get the posteriors to match. Of course, you do a lot of other types of checking, but that was a good overall, that you actually work on realistic data sets that are very different, and you get your model working. So then you end up with a bit more complicated model where we have implemented the theoretical model and some kind of parameters. So what we do, we actually learn how to get your model working. So in theory is a very nice way to write your Bayesian models and do inference. But in practice, it's often very hard to get it stable running in production. So even today in the morning session, you saw that you get a lot of warnings or something that something doesn't fit. So, and if you want to run that automatically, so you are almost guaranteed to face some issues when you run it. So I would even say that, okay, you can see that Stan is designed from more the researcher perspective. It's going towards the productization. There are maybe languages that come from different angles, so more from the developer side and improving on the coding, like this PyMC3 or TensorFlow probability. They, at the time when we started, they didn't have all the functionalities. I'm not sure whether which one fits your case better. Stan fits our case very well now, but it's also good to develop the other alternatives. But with Stan, I would say that it's very good to limit the scope of the model. If you want to run it in production, so have a very specific use case that you can make sure that it works and it then scales to all different data sets we have. And how to get it working is to all those kind of tricks that you can learn. So reparameterize, so maybe that the distributions are not they are 0-1 normal distribution that you scale, or something like that. Use very reasonable informative priors. That was discussed also in the morning. So you should actually give the priors that we know. We know, for example, that revenue is a monetary unit, so we know more or less the scale of what a single ad can cost. So you should bring those informations there. Because especially we see also cases where there isn't much data, so the model should fit also those cases and give reasonable results. And we, for example, from our use case, it makes sense that if there is not data, we want the campaigns to actually give the same revenue per conversion. So we want to be conservative. So then we can bring that into the priors as well, so that if not enough data, be conservative. And that helps also in the convergence. And also, actually, custom initialization was something that we found out that, especially in those cases where there are not much data, so sometimes the random initialization fails to converge, so it was actually easier to do a bit more initialization, which is more narrow, so more closer to us, not so wide, so then don't sometimes hit, end up out of the possible range. So then, okay, the sampling is the default, so Stan has this HMC, which is very nice sampling and of course produces the good results, but it's some cases too slow. So for example, when we have cases where we have just few ads, then the sampling would work, but then if you have 10,000 ads and you want to run it daily and get it out, then you have 1,000 other cases, so then it just cannot wait for one day because you wanted to get the results in a few minutes. So then there are other alternatives. So there is this kind of variational inference that basically approximates your posterior distribution with some other distribution. So that actually the reason why we took Stan into use was that this ATWI came out, was released 1.5 years ago. So I think that was the reason why we started, because now we could be able to run something in production fast enough. But the issues is this kind of approximation that they don't always work. So when you run this approximation, it goes much faster, but you should of course validate that you get the same result than what is the sampling giving. So you could say that sampling is the truth that you should trust, and you should just validate that the ATWI variational inference gives the same results. There is this maxima a posteriori, very good point estimates, but they are not in our case useful enough because we need real uncertainties and be able to sample. There were also some issues with this ATWI. So then, what we found out that when you run in production daily, so sometimes there is fine-tuning of the parameters in the beginning. Sometimes that failed for us, maybe through the initialization. Then we just find out that there is some parameters that are just easier to fix and not let the ATWI to find them again. So you could say that now what we do, we have about like 1,000 euros, maybe 10,000. I'm not sure actually, I haven't checked, but like the scale, like through this budget allocation, about 1 million euros daily is spent, so that some money goes via this kind of allocation. Not all cases are using this revenue optimization, but something is used. So it's quite massive scale already. So how we do it is we use Bayesian actually interface. So there is a lot of surrounding Python code to wrap that, so that we are safe. Also data handling and processing. We use for scheduling, we use Celery. We have a lot of monitoring going around. If something would fail, we would just revert to conversion optimization, so we would skip the revenue. But so far, actually, I'm quite surprised. So it's been running smoothly for over a year. We haven't done much modifications for that. So the other parts we have been like considering implementing optimization somewhere else. But it's been running smoothly, so you could say that you can get the stand working in production. But then it's just limit the scope, may test very well, bring a lot of automation and validate it again. So just to give you an idea of what are the like results from this kind of model. So now this is just for the revenue per conversion. So of course the revenue per spend differs, but so there is the campaigns differ in the amount of purchases that they bring per spend. But then if you look at the revenue per purchase, so that's now what we are interested in this model. So very common case is that your campaigns or ads don't differ in the revenue purpose, because that's so far from your advertisement. So, and that's what we wanted to get rid of, so that people don't overreact to the random numbers that they see. So, some kind of plot, so there are those like raw numbers and matched numbers, so we get that every campaign has similar performance. Then there are some cases that your campaigns differ, the ads inside that campaign don't differ. So maybe you have where the hierarchy brings information, and then there are like cases where there's a lot of data and the actual differences in your campaign. So then we can identify that and use the results. Okay, that's actually my part. So thank you very much. And if you are interested, so we are currently also looking one senior data scientist who would know a lot of Bayesian modeling. So I'm mainly in Helsinki, but we have a lot of opportunities elsewhere as well. So thank you.
Hi, my name is Anna. I'm from Lendable, and I'm very excited to be here today and tell you a little bit of what we do, how we do use Bayesian models and Stan in particular to kind of in our daily life. So a quick overview of what I'm going to talk in the next 10 minutes or so. I'm going to give a quick introduction about what we do and kind of what our problem is and how we solve that and how we use Stan. So Lendable is a startup. We are an upfront debt capital for alternative lenders platform in sub-Saharan Africa. So we are the link between investors in the US and Europe and so-called alternative lenders in East Africa. Alternative lenders are non-deposit taking asset-backed finance institutes or credit institutes. So for example, we have customers that lease motorbikes for taxi drivers, or I think we looked into some business that lend cows for like agriculture purposes, or solar panels to get people access to electricity. So this is kind of part of the impact investing movement. And what we do is basically we look into a customer and then purchase part of their portfolio, which gives them capital to grow. And we purchase the right to receive the repayments of loans on motorbikes, for example. It's called receivables financing. Another part is that we do some data analysis and build analysis tools for our customers to help them maintain their portfolio and also for ourselves to kind of keep track of everything. So our problem, so to say, is that we want to predict those repayments. We want to predict cash flows. There are problems that come with that. Let me quickly, oopsie. let's go back. We've seen that we want to perform our models on a loan level, so each individual loan gets its own kind of tracking line. And we want to really be very careful about co-movements. We've seen that before, that individual loans, especially when they're defaulting, if the economy is kind of bad, there is some correlation. And we want to be really careful about that because it can mess up a lot. And then we have the problem that we have time series. And if you want to predict more than one further step in time, your predictions become your predictors. So the model of cross-validating that has to be kind of overcome. To quickly give your heads up, those are the reasons why we use STAN and Bayesian model in particular. It allows us to model efficiently unusual likelihoods. And the second part is kind of how we pitch that investors. Bayesian modeling allows us to incorporate things, uncertainty that we cannot see in the data. So to give you a quick overview about what I'm talking about. When modeling cash flows, when modeling repayments on the loan level, there are certain things that you have to consider. So there are economic shocks that you want to incorporate into your model. You want to be very careful about correlation, which we have seen across our customers based to the similarity of their collections efforts, for example. And another big part is that we cannot really observe heavy shocks or the scale of the shocks in the data, because usually when some things like that happen, you don't have any data anymore. Yeah. And so Bayesian modeling allows us, or STAN allows us to do that efficiently, to kind of model this co-movement, which allows certain parts of the portfolio to kind of move away from like the median case or something, and parts that kind of stick to it. And this can be rather tricky and hard and complicated to do with so-called classical methodologies and techniques. So what do we need? Like at the end of the day, we need to kind of calibrate well uncertainty into our model, and we the most important thing, or the kind of main problem, is that we need predictions how much is going to be paid back at a certain different point in time, big T, for example, which might be 60 months from now, which is kind of a very long time. To show you a little bit of what I'm talking about, this is a monthly plot of some scaled version of how much is going to be repaid over time. And so each line is like a cohort of loans that originated, for example, in the same month or something else. And we see some correlation there. For example, what we've seen, especially in Kenya, for example, is that at the end or at the beginning of a school year where school fees are due, repayments drop. Those things, for example. So there's a time component that you want to incorporate into your model, or that we want to incorporate. And the other thing is that kind of the likelihood or the density of what we try to model at the end of the day is far away from being normal. And so what you can see here is the density of kind of the proportion of what was actually paid versus what was due. So some of our lenders, they have like a weekly or a monthly schedule. For example, this is a weekly schedule, and you can see the weeks here. So the due payment is what was due in a week, and then it's like half of it or like a proportion of it. And on the left-hand side, you see those who just didn't pay. So the likelihood that we end up with basically is combination of discrete and continuous. So it's kind of not normal. And Stan comes in here very, very handy. I cannot, or at least I don't know, about any other methodology or kind of software that does that in a very efficient way. The other thing that I quickly mentioned in the beginning is that when you predict time series outcomes over multiple time slots in the future, your predictions become predictors. So you have to be really, really careful about back testing those models. If you want to kind of do that, it becomes computationally very, very expensive. And we use a combination of R and Stan and Python to kind of do that. And the handy thing here is that we can incorporate Stan functions into our R scripts and just kind of tell R, please do simulate, and without our developers to need to learn C++, but we can kind of expose Stan functions into R and efficiently simulate our models. And this kind of brought us to an enormous speed up compared to R and Python. Especially because these functions are easily parallelizable. So for example, with 8 cores, we had a 4K speed up in running simulations by exposing Stan functions into R and kind of just let it kind of simulate, which comes in very, very, very handy, at least for us. And now I'm gonna kind of quickly talk about how we actually do all that kind of stuff, right? So we have one baseline model. It's the model template, which is basically a zip file. It contains the Stan script that runs the model. It contains some R scripts to prepare the data. There are some alteration to some customers. Not every customer is the same. So those R scripts sometimes have to be updated, but usually the model template kind of basically stays the same. Oh, and it also has functions to simulate the model. Each model template is the basis of a model estimation. So for each of our lenders, we can estimate this repayments, this cash flow and defaults model. And based on this model estimation, we run back tests. So we are back testing every single model estimation to be kind of sure that we're doing the right thing. And I will quickly talk about that as well and show you some pictures. If we say, okay, the back test looks good, we also look at some kind of evaluation metrics. We kind of approve the model estimation and can run simulations. So we've built an R library that allows us to expose Stan functions into R and kind of simulate a model efficiently. We can also do a bunch of automated visualizations that allow you to kind of quickly see, is it doing the right thing? And do backtesting in a proper way. And if we say, okay, the model looks good, the simulations are looking good, there is no further need for, sometimes we have to make some alterations when something is severely different from what we're used to, which is not often the case. And if we're all done with that, we can run portfolio simulations. So as I told you before, we are not buying like an entire customer and entire lender. We are purchasing a part of their portfolio. So we can run portfolio simulations, and we have some criteria for loans in kind of in the Lendable portfolio to be met and kind of to be part of that. And so once we have the model estimation and simulation, we can run the portfolio simulation only on those loans that we find fitting for our criteria. And after we've done all that, we have kind of the final output is we can aggregate that up for the portfolio to see what can we expect in a median case, in an upper case, and a lower case of cash flows and repayments to come back. And then we can put that in front of the business team and the investment team, and they can say, then they say, okay, let's price it like ABC. And kind of to secure, kind of close this whole process. Yeah. And this is my favorite slide. So we have here a similar, very fancy or unusual likelihood. And the orange lines are the posterior applications. So those are our backtesting simulation, kind of automated pictures visualizations that we get from our backtesting. And this is one of the visualizations that we use to evaluate if we're on the right track, or if the model is not fitting, or if the model is not a good fit at all for our purpose. So to kind of sum it all up, my favorite slide again. So Stan allows us to efficiently and very carefully model unusual likelihoods. We got a huge speed up compared to R or Python. And in general, Bayesian modeling is kind of allows us to incorporate like those shocks I talked about before that we cannot really see in the data, but we know, like in the back of our heads, that might have an issue, and there's some uncertainty that we want to incorporate, right? And yeah, so that's the most helpful thing. And that's actually something that I came across a lot lately when you talk to, especially, in general, non let's say tech people or non-statistic people, convincing someone that especially this kind of modeling is the right way to do, or that this is how it should be done, in our opinion. This is the main argument that gets people. If someone is like very, very stubborn about how modeling is done or how the world should work, you cannot sell anything or any model. You cannot explain anything if another person is that stubborn. But in general, if the person you talk to understands some part of modeling or kind of some part of information and how data comes together, their argument that you can incorporate information that you might have into your model, into your beliefs, and what you do at the end of the day, without kind of having to, without knowing if it is in the data or not, or with knowing it is not in the data. This is the kind of go-to argument that we've seen works the best when convincing that the Bayesian modeling should be everywhere. Yeah, and that's it for me. Thank you very much.
So the only person who didn't do a presentation is Tom, so if I could maybe ask you to tell us a bit about what you do and how do you guys stand in your environment?
Yeah, thanks. Can you hear me? I'm Tom Wilson. I'm a data scientist for Tweak.io, which is a software development R&D lab. We have a number of large clients across biocomputing, pharmaceuticals, a lot of blockchain stuff going on. And one of the projects I'm working a lot on is a fintech company providing digital financial advice. I'm using Stan in all sorts of projects, from projects where you have to run Stan very quickly in small projects to where you're just running Stan whenever you feel like it, once a week, maybe a larger model. So yeah, it's been great for estimating time series models of pharmaceutical problems.
Thanks. So maybe I'll ask Markus, what were some of the original impediments, I guess, to adoption? Like, how did you guys, when you started implementing Stan and you thought about, productizing this workflow, what were some of the initial pains and how did you overcome this?
Yeah, so I think we wanted to use Stan even before there was this variational inference, so when the sampling existed. So then the biggest pain was already that it was just too slow for our scale to use. So when the advi came, so we were very happy that, hey, now we could actually be able to run something in production scale with our data fast enough. But still, like, the pain was just like getting it actually working with all different types of data. So I think that project, from when we started, it took maybe 4 months from like the beginning to actually have everything running in production smoothly. Of course, maybe the intense modeling part was maybe one month doing those and testing. So, but it was, I had used Stan before, but still like getting it work, everything is surrounding. So there was just like in Stan one line and one parameter can have a huge impact. So it's quite fine tuning to get everything working smoothly.
So I'll ask Anna. So you, as far as I understand, came to Lendable when some of this infrastructure was already in place, I think. And so you had to sort of learn to work inside of the existing environment. So what were some of the challenges for you starting to work in the environment that uses Stan
Well, first of all, to kind of collect all the information that you need to kind of get to know a system can be sometimes tough, because like this person is a special knowledge in this environment and that environment. The most tricky part for me was to understand the connection between Stan and R and kind of how I can personally leverage that, as well as most, like the whole web application where we run the models and the simulations is hosted mostly in Python. I have very little knowledge about Python, and kind of those the connection points are the most difficult points to kind of Stan and R. That is kind of the same at some point when you're trying to understand it, but how R and Python communicate is sometimes very, very odd and very tricky to see through, basically, and kind of. But that comes with time, and that I've really enjoyed kind of learning this very, very well thought of structure, and it kind of has grown over time to kind of get that knowledge about edge cases and use cases where, for example, my boss Jim already knows this won't work and can tell me kind of don't do that. So this was really helpful. But yeah, so that's the main points.
Another thing, I wonder, maybe Tom, you can comment on it, or if anyone else wants to, is to work inside of this environment, inside of Stan and other probabilistic languages. It's not a lot of people have these skills, right? And so, oftentimes, when recruiting, you have to find some approximation to a person who has all these skills is likely you probably won't find exactly that. If you had some experience with that, how do you go about finding the people? What's the ideal background?
Well, I had a great guy working for me who had a background in theoretical physics and actually understood quite a lot of the Hamiltonian simulation. But he just understood it as simulating the trajectory of Hamiltonian mechanics. And although some of the vocabulary clashes, I think that made it really easy to transition and start with Bayesian, even though he didn't know statistics, but starting with Bayesian inference and actually picked it up really quickly. So I think that is a great background. If you don't have a background in statistics, then kind of theoretical physics. I think scientists in general make really good data scientists. Yeah, that's definitely something I'd look at recruiting again.
Okay.
Yeah, I kind of agree on that. So like, you need to know that have math background, whether it's theoretical physics or something else. So that gives you the solid understanding. Of course, it's preferable that you have been doing some Bayesian stuff. For us, because we are like a web development company, we are actually, or we were looking more like unicorns who know both software development and like Bayesian analytics very well. So there are rare people who know both sides very well. So now we have because company has grown, so we can just look people who know more about the Bayesian model and are willing to learn also development and are interested in solving the customer problems. So. Cool. Yeah, but still from the same kind of background, I think is ideal.
Any thoughts on that?
Well, I studied mathematics, and kind of the first thing that we were kind of taught basically is, or told in the first couple of months, is that you're not learning like a specific, and you're not really learning or being taught a specific formula or this is how kind of it works or something like that. When you're studying mathematics or physics or something like any more science field, you're being taught a way of thinking, a way of problem solving, how to tackle things and kind of how to structure problem solving in the end. And I think that really helps both with statistics, the Bayesian workflow, and computer stuff in general.
Okay. Anybody tried converting a frequentist into the Bayesian?
I succeeded with myself.
Oh, you did.
So that's like I did my PhD on frequentist topics. So, but that's luckily 8 years ago. So then you realize that what did I do?
Congratulations.
Yeah, but life has changed.
Okay. All right. Well, let me turn it. We have a few more minutes. Maybe we can turn it over to the audience and ask if anybody has a question. Oh, let's take one from the front.
Hi, this is Markus. So
Yeah.
you guys said you were fitting, thousands of models a day with the PDBI. Do you have any sort of automated diagnosis or checking of model sanity that you do for that?
Yeah, we have some very simple that like basically the outcomes of the model give good results, and of course there is this like the ad gives already like that it has converged. Also we run those. We have some kind of rerun that if something fails, so then we rerun it automatically again. But mainly it's been that when we have been just running it in many cases, it has worked and we have fine-tuned. And of course we have logging in place, so we have been looking that if something has failed, so then analyzing why that case failed. So we basically log all of the input and output data that we get. So then all of the like logs from the advis, so that we could go looking for specific cases. But surprisingly, for 1 year we haven't had to that specific revenue standpoint. We haven't had to look, so it's been working since quite well. Of course, initially there were a lot of those minor things that we needed to fix.
Okay. Anyone else? Yeah, Aaron.
Right. I actually have two questions. If that's okay. So one question relates to the advi.
Yeah.
Like, can you explain a bit how the transition, how much effort that was actually to convince yourself and all the people using this tool to actually go away from MCMC to variational approximation? Like.
Yeah. So for myself, it was basically okay. From tool perspective, you just like instead of saying sampling, you say that use VI. So that's like from tool perspective, it's very easy. For like why we did was basically that the sampling was too slow for those big data sets that we have, that it wouldn't converge in the time that we basically, because we want to do decisions every day and get the budget changes. Actually, you should do those during midnight, so there is not much time, and we want to use the recent data. So that was just like constraints that we need fast algorithms to do it. We could of course implement stuff ourselves and do that kind of variational approximation, but because there just came this nice advi, so why not give it a try? So it wasn't like our company is something that I just want to do it, so then you just do it, and you don't need to convince anybody else than yourself and see that the data gives that it works basically.
Angie, go ahead.
I have a question related to the productization of STEM. And has there been any attempts to apply STEM to like logistic areas? Because I've been working with the pallet rental company in South Korea for several years, and I think logistic and SCM is a very good
SCM, you mean supply chain management? Is it? Yeah, and logistics industry. Anybody has a comment?
No, I think it sounds like a great idea.
Yeah, no experience at least.
We were contacted a few years back by I think by a logistics company to do some work. We didn't end up doing it. I think that people are trying, but perhaps this panel is not best to answer that because we work in pharma. These guys do finance and ad marketing. So, yeah, in the back.
Can you talk a little bit about, does your team push any PRs? I can imagine like a running compute model for Stan, so you don't have to recompile the entire model, train it over the entire data set every single time. If you want to update, like as new data or streaming data comes in, maybe that functionality doesn't exist today, but that would be something your team might want. Do you guys actually have time to contribute and push back and get back to the community?
Yeah, that would be very good. So for, of course, like if you look how to make it fast, so the Stan model needs to be pre-compiled. So we have like GitHub integration and deployment. So whenever we push something new in the deployment, so then we pre-compile the Stan model at that time. So we have a compiled model in the server which then runs the actual sampling. So, but we don't surprisingly use historical like the previous model fits. So we just like take the recent data. Now we are maybe taking the last 14 days and use something there and just fit the data with that. So from scratch every day for every account, basically.
Okay, please go ahead.
Yeah, this is maybe a question for all of you because you work, maybe some of you want to answer, but you work to a different degree, I guess, with kind of a basic model that you maybe adjust per customer. I was wondering if, to what degree you're doing this and to what degree you're involving the customer in like, you know, adjusting the priors maybe or adjusting the model itself for each customer separately.
I'll answer for us because I think I think we do that maybe more than people who work with very specific use case. Of course, we try to get a model that fits everybody, but for us, it's very, very hard, right? So in pharma, in clinical research, you know, there are, so far we've always had to, you know, incorporate some additional information into a model, particularly because when we work in a specific disease area, a pathway of one disease may be different than another, and you know, for us, we spent some time with either biologists or clinical researchers to gather this information pretty early on, right? And so sometimes we have to read literature on the subject to get some reasonable priors. Often we have to elicit that information directly from people who have done this trial in the past. And so it's kind of an iterative process. But in general, structurally, like our models are similar, right? So if we are, you know, doing stuff in like phase 1 research, you know, the observation is usually the same, right? It's we're measuring concentration of compound in blood over time. In later stage, you know, the structure is maybe also similar, where we have now some survival data, some hazard data, but then we have some biomarker data, and so structurally they're similar, but in terms of the mechanistic or semi-mechanistic part is often need to be tweaked. Yeah. I don't know if you want to comment on it.
Yeah, for us, it's a little bit different. So our baseline model stays more or less the same. We have an awesome data team that talks to our customers, that kind of works, they sit together kind of side by side and kind of tweak the data until it fits our format. And this is what I'm really, really glad and really appreciative about it. I get kind of the clean data in the format that I'm used to. So sometimes what needs to be done is that Some variables, for example, mean different things to different customers, so we just have to tweak that a little bit. But that is usually done when preparing the data for the model estimation. The baseline model stays more or less the same. Where we work more closely with our customers if they ask for specific analytical tools for their portfolio management. There we really also sit together in multiple sessions to kind of work that out and kind of include their knowledge into kind of our framework and to kind of have this back and forth. But that is not the usual case for us.
I would also comment. So we do productized analytics. So basically we try to build just one model that works for all. And that's basically very challenging because we have very different types of vertical, different types of customers. So how you can build something that works in all cases automatically. But we still work very closely with the most advanced customers actually to get the feedback. So you could also say that we have this revenue optimization in place, but it's somewhat wrong. It doesn't work for all of the customers correctly. So we, for example, we have no one case where it doesn't work. So currently we estimate that revenue is positive, which sounds like natural assumption to start, but then some customers come to us, hey, people, if you're e-commerce, people return stuff back to the e-com, and that actually generates negative revenue. So we just exclude that data, but we should improve the model. That, of course, if we improve that in the model, it will help also other customers who have faced the same issue, and that's the goal. Whatever we do, we want that it would solve the issue for all of the customers, but at the moment we don't do customer-specific models.
Let me just comment that in finance there's something called the black letterman model, where you can ask the customer to give expectations of the growth in different stocks, and then you can sort of do a trade-off between what you think and the customer thinks. So it's not exactly a prior, but it sort of works a little bit like that. That's a theory that's been developed for some years.
We have time for one more short question. Anybody wants to? Go ahead.
I don't know if anyone has had trouble with updating their models. So like right now, if I'm fitting a hierarchical model with 1,000 people, and then tomorrow I get one new person, I have to fit the hierarchical model again from scratch, which seems a bit wasteful given that like the final answers should be very, very close to the answers they had yesterday for the first 1,000 people. And I haven't really found a good answer or a good way to deal with that, so just wondering.
If you do find a good answer, please tell us.
We're working on it.
Yeah. It's something that like Bayesian inference is clearly lends itself to that kind of analysis, right? And so in principle, if you can capture a posterior distribution in some kind of parametric form, you should be able to use it for the update. We haven't done it, and I think you said Jonah is mentioning that they're working on some tools to make it easier.
Yeah, or various very good approximations in certain situations.
Yeah.
To then be able to feed that into as an input to the model.
Anyone else has a comment on it?
Yeah, if I can just add, if you're happy with the Laplace approximation, but with a covariance matrix, then if you can run DFGS, then you can cache the estimate, the Poisson-Nielsen estimate, and then you can use that as a starting point for the adaptation parameter of the DFGS on the next, when you add more data. And that can work really, really well. So you can get a linear, as you add one more data point, then you just get a linear, or in fact, even sometimes your inference time can build out because you start from better and better starting.
Cool.
And the one that's not basically, you can do a multivariate normal approximation to the posterior unrestrained space. And if that's a suitable approximation, then you can feed the vector and covariance matrix in as a prior.
Yep.
Yeah,
But there's other more sophisticated things that are better in theory, but
I can sort of understand how that works for like the 1,000 by 1,000 matrix, but what about that one extra row and column?
not in principle should work for that. I mean, even the approximation stuff, you should be able to update with one observation if you already have a pretty strong enough prior based on fitting to a lot of data.
All right, that's all we have. Thank you very much, guys, for coming. Appreciate it.